What to work on next, chapter 11.1.
God.
No.
New things.
Okay.
I don't need that. I do not want it.
I have to at some point, anyway. I've only done like one
Here's the proposed chapter 1, 5, 2,
We got a ways to go, people.
Okay.
When I go to take that test, if I don't get it, then I'll do that homework. Refresh my memory
Yeah.
and kill it at the same time.
Okay, let's talk about compound interest. Suppose a sum of $500 is deposited in an account with an interest rate of R% per year, compounded monthly. At the end of 10 years, the balance in the account, as illustrated in the figure that's going to be on the next slide, is given by A equals 500 times 1 plus R over 1200, all raised to the 120th power. So this is straight out of your finance math from Math 1630. It says find the rate of change of A with respect to R if R is equal to 5 or if R is equal to 7. And this is the graph that we have of A. And what you see happening, of course, is the way that compound interest works is you start out with your base amount and then it steadily increases. And it increases at an ever-increasing rate. Its rate of change itself is constantly increasing because you're not only gaining interest on the original amount that you deposited, but on the additional interest that you've accumulated up to that point. So you're getting interest on your interest. So where the problem says find the rate of change of A with respect to R for R equals 5 and R equals 7 means that we need to find first the derivative of the formula for A. And that is going to be chain rule problem, right? So if we remember quickly what chain rule says, going back to the problem above it, in the problem above it we have a chain rule problem mixed with a multiplication problem. So in the problem above it, the part that was chain rule was this part. Because we had something inside a set of parentheses, and the outside of the parentheses was a power, so the outside function was something raised to the third power. And the way we took that derivative was we brought the power down in front, and then we kept what was in the parentheses just the same, and then we reduced the power by 1, going from 3 to 2, and then by the chain rule we also have to take the derivative of what was inside the parentheses, which was 5. So the derivative of 5x minus 1 to the third power is actually 15 times the quantity 5x minus 1 squared. And that's similar to what we're going to do in this next problem. So what we have here, this is a constant, so it's just a multiplier. It's going to come along for the ride. It's not going to do anything else. So A prime of R is going to be 500 times the derivative of what's coming next is something raised to a power. So that the outside rule or the outside function is the 120 times what's in the parentheses and then reduce the power by 1, which makes it 119. And then we have to take the derivative of what's inside the parentheses. And the derivative of what's inside the parentheses, the derivative of 1 is 0. And the derivative of r over 1200 is going to be 1 over 1200 because that's 1r over 1200. So when we multiply all of this together, we have the derivative of a with respect to r. And that derivative is going to be, let's see if we can't get it all together here. 500 times 120 over 1200 for this part. So that took care of this, this, and this, all times 1 plus r over 1200 to the 119th power. So if we completely clean it up, a prime, which is the same as dA, dr in the other alternative notation, let's see if we can get a little more light on this thing, is going to be equal to, let's see, divide top and bottom by 100. 12 goes into 120 10 times. So 5 times 10 is 50. Times 1 plus the interest rate over 1200 to the 119th power. And then to get a prime of 5 and a prime of 7, you simply plug in 5 and then plug in 7 to that. And we're going to verify that we did this correctly by actually getting the calculator to do the derivative as well. So first of all, we'll calculate what we think is the right answer, which will be 50 times the quantity, 1 plus parentheses x divided by 1200, close parentheses, and close the parentheses again and raise to the 119th power. And we're going to go back and replace that x with, first of all, 5. Oops, lost my calculator. And that comes out to be 82.0087, so we'll call that about 82. What would the units be on that rate of change? A is measured in dollars based on the interest rate. So what would A prime be? Dollars per year. It's rising by $82 per year at 5 years. Okay? That's how the amount, the principal, and the, well, what I guess we would normally call that the future value, because that's what it would be at that time at 5 years in the future. And then A prime of 7 would be similar, except we'll substitute 7 instead of 5. So at 7 years, we're increasing by almost $100 per year, $99.90. Is the rate at which our future value is increasing at that point in time. Now, if you want to verify that those answers are right, the easiest way to do it is to use your math menu, go down to NDeriv, use your formula, which is 500 times the quantity 1 plus the interest rate divided by 1200, all raised to the 120th power. Let's see, we've got 1, 2 sets of parentheses open. I think we need another one. Yes, we do. Need one in front of the X. So there's X over 1200. That closes that set of parentheses. That raises it to the power. So we should be good to go. So then we need a comma, an X, and then what value of X we want to use. So this is going to be 5. And we get the same answer that we did before. Let's see if I can get that down out of the ceiling a little bit. Okay? And then if you just want to repeat that and change the 5 to a 7, we verify that it's $99.90 in 7 years. Okay? So you can check your answers if you have numerical answers to check them against. You can check and make sure that you did your derivative correctly. What the calculator won't do for you is it won't do the algebraic derivative for you. But it'll let you verify some numbers to make sure you did do that derivative correctly. These homework problems here, that is not the correct page numbers, but it's the problems at the end of section 12.3. So does anybody have any questions on this one before I go on? Okay, not hearing any. Let's begin 12.4. 12.4 and 12.5, we get into derivatives of something called the transcendental functions. Transcendental functions are exponential functions and logarithmic functions. Would also include sine, cosine, trig functions, but we don't get into them in this class, although they are of some benefit in businesses where things are cyclic. A lot of times a sine or a cosine curve does work well to model data in some business worlds, but we just don't cover it in this course. So we're going to start off with definitions of the derivatives of exponential and logarithm functions. We're going to start with exponential functions. And first of all, we're going to look at the fact that the derivative of e to the x is going to be your favorite, because the derivative of e of x is itself. It's its own derivative. So not hard to remember. The derivative of a to the x, on the other hand, is a to the x times the natural log of a. These two are actually the same rule. The only difference here is that the derivative with respect to x of e to the x is e to the x, just like it's a to the x, but it's times the natural logarithm of e. And what is the natural logarithm of e? What is ln e? Oops. So the natural logarithm of e to the first is 1. So this is really 1 e to the x, which is what makes it just e to the x, okay? So these first two rules are actually identical. The only thing that you need to be concerned about on the second part of the rule is that a can't be 1 because the rule won't work when a is equal to 1. Now, you can have the power on any base, whether it's a or e. You can have the power actually be a function of x. And in that case, it's a combination of chain rule and these two rules. So the derivative of a raised to some power where that power is a function is going to be the natural log of a, just as it is here, times a to that power, just as it is there, but then you take the derivative of that power and multiply by it. So it's chain rule again. The same thing if it's e, the derivative of e raised to some power that's a function is e raised to that power, because the natural log of e is 1, times the derivative of that power. So this time what you'll take the derivative of is the power. Unlike before where you took the power down in front, reduced it by 1, and then took the derivative of what was inside the parentheses, this time you'll have to actually take the derivative of the power. So we're going to do some examples. So we have y equals e to the 5x power. And the derivative of e raised to any power is equal to e raised to that power. But then I also have to take the derivative of the power, and the derivative of 5x is 5. So the derivative is actually 5e to the 5x. Does that work for everybody? This thing just gets worse and worse. Any questions? Okay, here we have a constant 3 raised to the power t. It doesn't really look like a chain rule problem because it isn't. So ds dt, or s prime, is equal to the natural log of the base times what you started with. Okay? The derivative of 10e to the 3x squared, we'll just do the y prime notation this time. 10 just comes along for the ride, it's just a multiplier, so it just hangs out. So the derivative of e to the 3x squared is e to the 3x squared, but it's going to be multiplied times the derivative of 3x squared, which is 6x. So in order not to have so many parentheses, you could also write this as 10 times 6x is 60x e to the 3x squared. Now hopefully those first three are fairly straightforward. Any questions? Anything anybody doesn't see where it came from or why it's there? Okay, what potential issues do you see in this next problem? It's a little more complicated than the others. You got a radical. Okay, we can fix that. We'll change it into a power. What else do you see that is different? You see one function there or two? You see two? You see two because this is a multiplication problem. This is the product of e raised to the x squared plus 1 power and 5x plus 2 raised to the 1/2 power. So we're going to have to take two derivatives and then swap them for their parent functions. So working first on e to the x squared, the derivative, since I know I'm going to need to multiply it on this side, the derivative of e to the x squared plus 1 is e to the x squared plus 1 times 2x, which is the derivative of the power. And the derivative of 5x to the 1/2 is going to be 1/2 times 5x plus 2 to the negative 1/2. And now I'll bring down the original functions where they go. This is going to be plus 5x plus 2 to the 1/2 power. And this is going to be multiplying times e to the x squared plus 1. And the plus sign is because we have a product. Now, can you clean it up? Yes. Do you have to? No. Just because you can doesn't mean you have to. If you want to clean it up, eventually it would look something like this. Let's put the 2 in the denominator for the 1/2. Let's drop this down into the denominator to the positive 1/2 power. And that leaves in the numerator e to the x squared plus 1, and that's it. Plus the second part of it, you could multiply 2x times 5x plus 2 and get 10x. Well, no, you can't because you got a 1/2 power there, so you don't want to do that. You're kind of stuck with 2x e to the x squared plus 1 times 5x plus 2 to the 1/2 power. Now, I'm sure that the wonderful algebraic alcoholic people at my math lab really would just love to make it look even worse than that, but I think that's good enough. I'm fine with this. Do the first step. Do your chain rule, do your power rule, do your product rule, but any more cleaning up than that, I'm just not into the factoring it out and canceling stuff. Too much possibility to make mistakes. If you can do this one, you know how to do this. Okay? Do some more examples. And I will warn you, some of these are sneaky because they're there as review, not as something new. Find dy dx for y equals 3 times x. What's the derivative? Just 3. All the way back to the first section. Okay? This is not to be confused with y equals 3 to the x. Its derivative is the natural log of 3 times 3 to the x. So make sure that you realize there's a difference between these two function. That x is not a power. It's just a regular old x. This one, you have a power that's a function. dy dx is equal to e to the power's its own derivative, so it's e to that same power. Then you want to multiply it by 3 times 7 is 21x squared. And then a lot of you would rather see that written this way, and that's okay. But either one of those is fine. And here we've got another one that's product rule. Two parts. So first we'll find the derivative of x squared plus 1 raised to the second power. There's its derivative, 2 times x squared plus 1 to the first power. And then we'll also need the derivative of e to the 2x e to the 2x is its own derivative times the derivative of 2x is going to be 2, so I'll put it in front. And then we'll bring the rest of the function down to go along with it with a plus sign between. So e to the 2x goes here. And x squared plus 1 squared goes here. And this is dy dx. And again, you can clean it up if you want to, but you don't have to. You can turn things around a little bit if you want to. 2e to the 2x times x squared plus 1 squared plus, let's see, 2 times e to the 2x is 2e to the 2x times x squared plus 1 equals dy dx. And I will tell you, for the sake of those of you that are going to look at what my math lab tells you it looks like, they're going to say, oh, we have a common factor. Let's factor that out. And actually, once I got that part factored out, I say, oh, wait, I've got another common factor. So what their final form is going to look like, and it's going to look a bit like what you started out with, is going to be 2e to the 2x times x squared plus 1 plus 1, or 2e to the 2x times x squared plus 2, which does look a lot simpler, but it doesn't look a bit like what you start out with. Okay? This is all algebra. That's calculus. I don't care about this. I care about that. But when you get confused, when they've done something like this, what they've done is the algebra. If you're not sure if you did something wrong, ask my instructor. Okay? This is just kind of a way of saying, you know, don't second guess yourself. If it tells you your answer's wrong, send me what you've got and let me look at it. And if there is a mistake, I'll help you find it. But probably their explanation of how they got to where they went is going to help you a bit. So that is natural log functions, and well, it isn't actually the natural log functions. We use the natural log in this. So this is exponential functions combined with chain rule. And we have one section left, and that's the section that Shannon and a bunch of you have been dreading ever since this whole course started, because it's the part about the dreaded logarithms. Okay? Everybody hates logarithms. Here's the good news. We're only going to look at 2 kinds of logarithms. We're gonna look at natural logarithms, which is base E, and base 10 logarithms, which are the common logarithms. We're not gonna look at any base 2 logarithms. We're not gonna do change of base formulas. We're not gonna do any of that other stuff. We're only going to look at how do you take the derivative of a base 10 logarithm or a natural logarithm, okay? And you're going to notice some things that are in common with what we just looked at, which is why I wanted to do both of these in one day. When we had a raised to the x power, when we took the derivative, we took the natural log of a as part of the derivative. Well, if we have a base a logarithm, which in our case is going to be base 10, then all we do is take the natural logarithm of the base times 1 over x. This can also be written this way. And the reason that I bring that up is because this is nothing but a constant. It is not a variable. Okay? And as it was before, if that natural logarithm, if that base is the natural log, the base e, when you take the natural logarithm of 1, this actually follows the same format. It's 1 over the natural log of e, because that's a base e logarithm, times x. But since the natural logarithm of e is 1, that's just 1 over x. So that's why really there's no difference in these two again, except that when you do the natural log of e, it just becomes 1. Whereas here, if you have something other than e, like base 10, then this would be 1 over the natural log of 10. Okay? So even though we've got a log here of 3, all you're going to do is take the logarithm, the natural logarithm of whatever the base is. You don't need to change the base formulas and stuff. So y prime is going to be 1 over x, because it's the derivative of a log function, times 1 over the natural log of 3. And it just looks cleaner if you write it this way. Okay? And if you're wondering why you have to do the 1 over, if you remember the other one, this is the inverse of what we just looked at with the power of the exponential functions. Exponential functions and logarithms are inverses of each other. So when you have the exponential functions, you're going to be multiplying by the natural log itself, but when you're doing the inverse, which is the log functions, you're going to divide by that natural log. That's the only reason for dividing. Okay? You can also do logarithms of absolute value of x. You can do a logarithm of the absolute value of a function. You can do the natural log of the absolute value of x, or the natural log of an absolute value of the function. And just like before, the only thing that's going to be different is you're going to go ahead and take your derivative based on it being a log function. And then you're also going to take the derivative of whatever this function is and multiply that along with it by the chain rule problem. So if you're taking the natural log of 2x squared minus 3 to the x, this is pretty similar to taking the natural log of just plain old x. The derivative, the way you would take that derivative is 1 over whatever x is, and in this case that's x. So there's the natural log part of it. But this is also chain rule. Because you're taking a function of a function. So you just multiply by the derivative of what's in the parentheses. 3 times 2 is 6x squared. So there's your dy dx, 6x squared over 2x cubed minus 3. And the only difference here is that the base is not e. So we have to actually include the natural log of 4. And it goes in the denominator with 1 over 5x plus 3x cubed. But you also have to take the derivative of what's in the parentheses, because that's your inside function. So this is going to be 1 times 5 plus 3 times 3 is 9x squared. And you can put it in the numerator or you can put it off to the side, whichever way you want to do it. Okay? And we are actually finished at this point in chapter 12. Okay? Now, given that we still have 45 minutes or so, why don't you go ahead and start working on the homework in my math lab while I'm here to help you. Okay?
Is there a next that's gonna be on 12 and 13 or just 12?
I'm gonna look ahead at 13 before the first of the week. If we are gonna go ahead and do all of 13, then no, we'll have a test over just chapter 12. If I decide not to do all of 13, I may go ahead and either have a test over just chapter 12 and put 13 and 14, or we could do 12 and whatever part of 13 we do together. It might be better to go ahead and have a test over chapter 12 sometime toward the end of next week while it's still kind of fresh in your mind, just to make sure everybody knows the derivative rules, rather than piling anything else on top of it. I'm kind of leaning in that direction.
It's probably like on Thursday for you,
Yeah, probably next Thursday. They'll give us a week to actually get through everything. You have some time to practice, do your review test, and be ready to take the test. And I seriously think next time I may do the test online, strictly online. Because I can check it, for this chapter, I can check it just as easily online as I can pencil and paper. Go ahead and work on your homework, and when you get stuck, raise your hand, I can help you.
Can I look at it?
Sure. Anybody that didn't get their test back that wants their test can come get it.
Thank you.
You did good. right there. Just trying to put these back in order in case somebody wants to do anything else. I'll never pick up that one. Yes. Mhm. Okay, I didn't see that. Cause all I saw was this, and I thought you were done. Okay. Well, make sure that you, look over it, make sure I didn't overlook any of the others.
I'll make sure it doesn't.
Okay. Okay, so, put your price up. Thank you for bringing that to my attention. get bogged down now with the first step. As long as you're shooting with that first step right, the rest should be okay. Get it? Let's see. Okay, yeah, you're trying to do this more product. That's what it's doing. So the derivative should be. Derivative from first time determines 3x squared. Not 7x. Not 7. And that's it. You shouldn't have to back it. Oh, I know why you were trying to factor it out. You're trying to find what tangent line is horizontal, so you're gonna have to either, you don't have to do it by factoring, you can just start right there. Because all you're looking for is where are the zeros, and that's what that line's for. When you take the derivative, please drop it back. Okay. That was trying converting it to a product as well.
Right, yeah, I can do this equation, it's been algebra.
Well, as long as you get your first step, do the first step, then we'll check that out. Before we try to do the simple line.
Just like that.
Yeah. And when you first put your answer in, go ahead and start out with a fraction, so that when you have to do the numerator, you don't have to come up with all the extra parentheses, you can put in just what you got. And not have to have an extra set around the outside of the numerator. start right out with a fraction. Now go ahead and put your fraction in.
Just like one over.
No, just do this. Because your answer's gonna be a fraction. Now type your numerator in just like it is. Without simplifying anything. And then just put your denominator in. Saves you have a lot of trouble struggling with the algebra. And a lot of the things that they do, algebra, they look at factoring and simplifying, it just makes it easier.
No, no, no.
And as long as it's equivalent, you're gonna plug a number into the calculator anyway, so don't worry about the algebra so much. So since you passed this, you should be good. You should be good. Well, and that's the way I do it, I always make the test on the quiz. Yeah, I think this one will be on. Yeah. And it's faster if you know what you made too, because you'll know what the bottom line is. Because I'm not gonna take anything away from you, it scores what it scores. But when I go in, I'll see something like, oh, I can see why they thought it was this and not that. Like on the graph, on the other test that has percentages where you have this curve, and it would get it down to like 1.67%, but somebody may have seen a different point and calculated it differently. And they would have 1.75% or 1.83%. Well, that's close enough. So I would go in and judge on that one, like, well, is it close enough? There's a lot of difference between 30% and 1.5%. There's not that much difference between 1.5% and 1.6.
So,
Okay.
on this chart, when I was getting all these numbers, I get this, when I was trying to type this one, I not before. Because that was, I saw where I was messing up on that. So on
You're
this.
ready to screen.
So, obviously, I'm good at factoring it to the symbols like this. So I'm dividing these numbers by 2, positive 2. So negative 8 divided by positive 2 is negative 4. So, why is it telling me that it's supposed to be positive 4? That's what I would like to know. I don't know where the negative sign was supposed to have gone. I just can't grab the glass and walk away.
No, we can't.
So,
Let's see.
I mean, I did all my other signs correct, so we're.
Eight X. So this is your negative 8 plus or minus square times 4 times 3 times 7.
Which changes to 64 minus negative. So it should be.
64 plus 96,
Yes,
which
so
is
it's-
160.
And then I was factoring in 60.
So 16, you go 4 on the outside, up to 10 on the inside.
I don't know what. One of the first times I tried this problem, I put in the correct answer, they told me it was wrong. And then I changed it slightly, because I was like, oh, maybe I was.
Yeah, that's the worst time.
So I put it in there, and of course, I was checking, so it totally wrong, and then it put the correct answer as what I said originally. Maybe I missed something. I don't remember now, because I guess.
I remember you telling me about wanting to do that before.
I just don't know.
Do.
I mean, and the fact that it just makes it negative.
Oh, wait, no, I see what's wrong, because it's the opposite of the negative B. Negative 8 is positive.
Oh.
And that's really the only place that you're messing it up is right there, so that's why. That's why. Because you gotta change the sign on the term.
I totally forgot.
And,
That's what I've been
yeah,
missing.
that's what you've been doing. Little bitty algebra
Yeah.
thing, not a calculus thing.
Oh my God.
This will be good out.
Yeah. Oh, what's wrong?
Oh, it's not a negative. Right.
You're looking frustrated.
Well, I was, but I missed minutes, and that's all it took. So
Oh.
I'm pretty good.
You figured out what you did wrong.
Yeah, just missed the next. So.
Okay.
Like the tiniest things.
Have any of y'all gonna see Aaron Sanchez? He is at the tutoring center. I'll try to look at the schedule and see that he is real good. And he's actually enrolled in my lab in my class so that he can actually see the problem before we're getting and can work through the
Did you ever figure out what the deal with that problem from the side?
Is this something you don't want to attention to?
No.
Block me.
No, I went back and looked at it again, and I thought, why is that not the right answer? Send me an email, remind me, and I'll give you credit for that one, because you should have credit for that. The answer
Okay.
was right.
Well, I mean, there was that one and then one after that. where you said not to, if I couldn't get it.
Just send me a reminder, and I'll give you credit for one, I
mean,
got
it's
stuck
good, very
on
well.
55, and it didn't even belong to 57, so I was trying to figure out what was wrong with 55.
Okay.
And it could be a programmer error, I don't know.
All right, as long as, cause I gotta turn it in, right, when we have the test, so as long as I can get credit for it.
Yeah. I don't have to have your test back. No, these are yours. Your policy calls like that on mine, saying it's use that for say, guys.
So I'm using the camera camera, but
Okay. The opposite of negative 6 is positive.
I like, don't forget that one of the homework files, and that's when I like, oh, 6.
Is negative times negative is positive. And that makes me do it. See if I can find that though, because it is so easy to make a mistake, even if you start out with you really don't know how hard it is. So easy to mess around. There is a software on your calendar. Put in.
So did you all right?
the whole thing. It'll come back and tell you what words. I don't think it'll tell you what they are in rap. At least you'll have an idea whether or not what you're getting is correct.
Did you read it? I like this one.
Okay.
Did
you send me something you were line to ask me when I have class?
Yeah, when I left, I guess.
Yeah, we were gonna, y'all got the day off?
Yeah, and I got here and I said, I told you when.
Yeah, we didn't have class.
I was making sure.
Hopefully you didn't make a trip out just for this class.
No, I had already had.
Okay.
Question on the S correction, as parking lot. You said you won't forget it all.
Yeah, but that doesn't mean that I didn't miss something.
Well, it's just this one.
I wondered, but I couldn't figure out how you got
I
that.
just, I guess my answer is.
all right. Yeah, I'm working on it, I'm getting out of, on that. But I can be on it, so I'm actually more.
Yeah. Yeah, because that's always no problem.
But it's a lot.
I'm actually like,
Did you? I don't remember seeing.
I
Did you
wrote,
make your
yeah,
scratch
yeah,
mark?
I had written it down, how I went about it, getting too late
Okay. I'll go in and change it as soon as I get back home.
And I don't want the poll.
When I saw that, I thought, I'm always positive without actually seeing everything. I'm sure.
I appreciate you saying that.
I'll give you that. Right away. I've already got it. They have a brother. Is that what the problem?
Yeah, I'll-
You want me to email you?
Yeah, send me an email reminder.
He's like, you said it.
I'm good after.
Not bad.
I thought it was done.
Huh?
Probably done. I'll take from the garage for the house.
Yeah, we're gonna do that. I just can't do that.
Go up.
I was supposed to get all this wonderful stuff done over fall break and I was in the hospital and stuff in the hospital, so I've been back and forth. Yes, I will. You'll have a great report as soon as I get one. Yeah.
Uh-huh. No.
How you doing? Good, how are you, bud? Very well.